Hello, this is Ms. Clausing. So today I'm going to talk about Algebra 2, the Unit 9 statistics. These are the Day 2 notes. This is our last day of new material for this entire year. So focus and you'll be done soon. Okay, so today we're talking about what's called NormalCDF, the fundamental counting principle, permutations, and combinations. Some of you may have heard of some or all of these concepts before in Algebra 1, but likely you probably haven't heard of them too much. Okay, so last class we talked about how to come up with the probability percentage using a bell curve, right? We talked about the bell curve and how we could use that bell curve using the empirical rule to come up with probability percentages for data using a normal distribution, okay? We also talked about z-scores and how this leads us to the formula for calculating any data, whether it's exactly falls on a standard deviation or maybe it's 1.3 standard deviations from our mean or 2.6 standard deviation from our mean, okay? Alright, we can also use something called NormalCDF function on the calculator to do this, to find that percentage that's represented by something, a data value that falls 1.3 standard deviations from the mean, okay? So using what's called NormalCDF in our calculator is what we can use to find that probability. So we'll talk about, these are the steps right here in this box on how to use NormalCDF. Okay, it's just a function in the calculator. All right, you'll notice here that our lower bound is represented by lower, our upper bound represented by upper. Remember, this is our mean. The mu symbol is mean, and this sigma is our standard deviation. Okay, so that's what the four values are when we get to NormalCDF. Okay, so let's do an example with it. So we have an example where, okay, interrupted. So problem 1. According to factory packs chips in bags with normally distributed weights with a mean of 12.4 ounces and a standard deviation of 0.15 ounces. Remember what we said last time, when we see anything that says normally distributed, we need to automatically think of that bell curve and that empirical rule, okay? Remember that empirical rule is 68, 95, 99.7%. And our bell curve, again, is drawn over here, right? Little example bell curve. All right, so we have a mean of 12.4 ounces. We know when it's normally distributed, our mean is right in the middle of the bell curve. So we could fill this in. Our mean goes right here. All right, and we have a standard deviation of 0.15 ounces. So I'm going to count up from my mean. So 12.4 plus my 0.15 gets me to 12.55. Right, I'm just adding 0.15, adding my standard deviation each time. Add it again. Gets me to 12.7. Add it again. Gets me to 12.85. Okay, and then I go the other direction, but this time I'm minusing my standard deviation of 0.15. Okay, so this gets me to 12.25 and 12.1 and 11.95. Okay. So we were pretty comfortable last class. We talked about if we wanted to know what percent of bags of chips fall within one standard deviation, or say they fall between, say we want to know what percent of chips fall between 12.4 ounces and 12.55 ounces. We know that's represented by this region here. And using our empirical rule, we know that that is also 34% of the data. So we know that 34% of chips, bags of chips, are between 12.4 and 12.55 ounces. That's what we talked about last class. Okay, so now this class we want to talk about, well, what if they represent, what if we're looking for the probability of a bags which contain 12.64 ounces or less? Well, 12.64 is about right here. 12.64 or less would be all of this area, right? It's everything less than that little dotted line of 12.64. Okay, everyone see how that's 12.64 approximately, right? A little bit above 12.55 and less than 12.7. Okay, I can't tell you exactly, since it doesn't fall on an exact standard deviation, I can't tell you exactly what percentage is represented by that blue area. So to be able to find this, though, we can use our normal CDF in the calculator. Okay, so what you're going to do is you're going to go to your calculator. Turn it on, maybe. Okay, let's see if I can move this over. Okay, so I'm going to go to my calculator. Get out of this. Okay. And remember to get to normal CDF, the steps are in that box above. I'm going to go to second, vars, and number 2, you'll see it says normal CDF, so I said hit number 2. Alright, and -1 e to the 99th is what represents negative infinity. So I want everything less. So my lower bound is negative infinity. My upper bound is 12.64. So I want everything less than 12.64. Alright, my mean, where's this number in red here, the 12.4, it was given to me. And my standard deviation was 0.15. Alright, so we just type all that in, and then we push enter, and we push enter again. So the blue shaded area is 94.5 rounded percent of the data, okay? So this blue shaded area equals 0.945, or which is the same thing as saying 94.5% of the data. Okay, so the probability of bag would contain less than 12.64 ounces is pretty high. It's 94.5%. Okay. All right, if you need me to go through those again, you can just pause the video, rewind it, and rewatch this segment of video. Okay, let's go on to the next one. Another problem. Okay, so this is kind of looking at it from the other direction. All right, so we're given this bell curve. Again, you will not be given bell curves on the SOL. You need to know to draw these. You need to know that all bell curves with a normal distribution have their mean in the middle here, and they're divided into 3 standard deviations above and 3 standard deviations below my mean. It's how normal distributions work. It's just the rule. Okay, you have to know that. Okay, so it says, on a recent Algebra 2 test, the mean score was 76. All right, so my mean was 76. Normal distribution, mean goes in the middle. With a standard deviation of 3.5. All right, so I'm going to add 3.5 going up my bell curve and subtract 3.5 going down. So this gives me 79.5, right? Just adding that 3.5. This gives me 83, 86.5. And going the other direction is 72.5, and 68.5, and 65. Okay, we practiced that a lot last class. Okay, on the graph to the right, so that's what we did. We labeled the mean and the 3 standard deviations above and below. All right, now I want to calculate the probability of scores 80% or higher. Before I do this, let's just shade in what is 80% or higher. Well, 80% is not an exact standard deviation. It's not exactly 1 or 2 standard deviations above. 80% would fall somewhere between 79.5 and 83, so somewhere right in here, right? And I want to know, this is about 80%, and I want to know the percent of scores that are represented above 80%, so this shaded area, above 80%. Okay, so again, to do this, since it's not exactly 1 standard deviation, I'm going to have to use normal CDF. Make this line more solid, okay? I'm looking for that yellow shaded area. So I'm going to go to my calculator, and I'm going to go to second, vars, normal CDF's number 2. Now this time, I want to know when my upper bound is infinity, I'm going from 80% or higher, and my lower bound is 12.64, or or sorry, not 12.64. My lower bound is 80. Okay. Okay, so my calculator, I need to go to NormalCDF, so I go to second vars. NormalCDF's number 2, so I hit number 2. And my lower bound is 80. Remember, I want from 80 and higher, so my lower is going to be 80. My upper is going to be infinity. Remember to put this in my calculator, I do 1. And then to get that E, you look right above your 7, the button above it has a double E in blue. Okay, so I'm going to push the second and the button right above the 7, right above your 7. That gets me my E. Again, you push the second, so your blue key, and the button right above your 7 gives you your E, and 99. Okay. My mean is 76, because that's given to me. My standard deviation is 3.5, also given to me, so I can push enter. And enter again. So 12.7%, if we round that, 12.7% of students scored 80% or higher. Okay? So remember, this shaded region is 12.7%. Scored 80% or higher. So here the answer would be 12.7% of students. All right. Again, let me write those steps down for getting that E. So when you go into your calculator, 1 e to the 99 represents infinity. Okay? Negative infinity equals negative 1 e to the 99, like we did on our last example. Okay? To get that E in your calculator, you hit the second button, and then the button right above the 7, which it looks like a little comma, okay? And then you hit the button that has a comma on it. Okay, it looks like a little comma. Okay, this button is above the 7. All right. And it has, this might help a few of you, it has an E right above that button. Okay? Okay, so there's another example of that one. All right, next, problem 3. Okay, I want you to pause the video and I want you to try this one on your own. Okay, and then you can come back to the video and watch the video of how to do it. All right, so pause the video. All right, so hopefully you did actually try this on your own. Watching me do it is not as effective as you actually trying it and kind of figuring out where you may not understand what's going on. So I really hope you tried it on your own, but let's go through it. Okay, so this says a factory manufactures keys for automobiles with a mean length of 2.5 inches and a standard deviation of 0.21. Keys that are plus or minus 0.3 inches of the mean, so from the mean, will be acceptable to use. Keys outside this range are rejected. So what percentage of keys are acceptable to use? All right. So let's fill in our bell curve before we get started. So we have a mean length of 2.5. So my mean, since it's a normal distribution, my mean goes in the middle. And then my standard deviation is 0.21. So I'm going to just fill in this little graph. So 2.5 plus 0.21 gives me 2.71. Right, this is plus 0.21. Then we get 2.92. Then we get 3.13. Then we go the other direction. We got a minus 0.21 to go one standard deviation below my mean, which is 2.29. And then 2.08. And 1.87. All right, but what I'm looking for is I want to know what percentage are plus or minus 0.3 inches from my mean. So minus 0.3 would be, so minus 0.3 would be 2.5 minus 0.3, which gives me 2.2. So acceptable keys are at least 2.2, which is about right here. Okay, so that's about 2.2. Okay, and they go up to, I'll write this. So 2.2. And then also 2.3 above, so 2.5 plus 0.3, which equals 2.8. Okay, so through 2.8, which is about, we'll say it's about right here. All right, so acceptable keys fall between these two green dotted lines. Well, they don't fall exactly on one standard deviation. So the only way I can find the percentage of keys that fall in this shaded region is by using NormalCDF, okay? The only way is by using NormalCDF. If they fall right on one standard deviation, that'd be pretty easy, right? Because we know the empirical rule, we'd be able to quickly say 34, 34, whatever other standard deviations it includes. But since we don't know, they don't fall right on one standard deviation, we have to use NormalCDF. So I'm going to go to my calculator. And go to NormalCDF, which is second vars number 2. Now my lower bound is 2.2. Okay, and my upper bound is 2.8. Okay, my mean is 2.5, which was given to me. My standard deviation is 0.21, which was also given to me. All right, so let's calculate. So 84.68, so 84.69%. So 84.69% of keys are acceptable to use. Okay, so that's not an awful lot of keys. Almost 16% of keys are not acceptable and they get rejected, right? 84%-ish about are acceptable and they are accepted values, okay? So this would be 84.69% are acceptable. All right, and it's represented by that shaded region there. Now you could quickly, kind of using our empirical rule, just so we practice and don't forget it, quickly estimate to see if this makes sense. Remember, the empirical rule says that this is 34%, this is 34%, and this entire region here is 13.5. So if we say this green line represents about half of it, then this is probably, I don't know, let's just estimate it's about 7. And again, we'll just estimate this is about 5-ish. It's a little less than half of that. Okay? So if we add up all the blue, this number, just roughly estimating, we have 34 plus 34% plus about 5. Again, these are very rough estimates, plus 7, which would give us 34 plus 34 plus 5 plus 7. Gives me about 80%. So 84.6% seems pretty reasonable, okay? So this gives me 80% just using my empirical rule and kind of just guessing and getting close, right? The only way to get the exact answer is to use NormalCDF, but I can use that empirical rule to kind of guesstimate what would be reasonable there. All right. All right, let's move on. So that's it for NormalCDF. The next topic I want to talk about is the fundamental counting principle. I'm not going to spend a ton of time on this. It's really just definitions. If we were to draw out a tree, I'm not going to. It says use a tree diagram. I'm not going to. Okay? I want you to just think about it. How many ways could you choose a sandwich, a side dish, and a dessert from this menu? Well, if we have 4 sandwich options, 3 side options, and 4 dessert options, the way you'd figure out the number of ways you can choose your lunch is multiplying how many of each option you have by each other. So 4 times 3 times 4 is 48. So you have 48 lunch combinations, well, we'll say lunch options that you could choose. Okay? So this is one type of probability question they could ask you. The key here, when you're multiplying how many options you have by each other, when you see a question that says, how many different ways could you do something? When it says that, how many different ways, put this in a color, how many different ways, that should be a key. You're multiplying your options times each other. Okay? This is just the math terminology for saying exactly what I just said. It's called the fundamental counting principle. You can read that. Example again, different example. If I have 3 pants and 2 shirts, how many outfits do I have? Well, 3 times 2 gives me 6 possible outfits. Okay. Again, another one. How many outcomes? That keyword, how many, I'm going to be multiplying it by the options by each other. How many outcomes are possible when you roll a 6-sided die and toss a fair coin? So there's 6 options here. When I toss a coin, there are 2 options. Multiply them by each other, 12 possible outcomes. Okay? Again, how many outcomes? How many outcomes are possible when you roll 2 6-sided die? Well, that means I have one option where I could have 6, or I have 6 options for the first die, times 6 options for my second die. So I have 36 possible outcomes. Okay? How many outcomes, again, how many outcomes are possible if I can choose between 5 meats, 4 cheeses, and 3 crusts for a pizza? Well, I have 5 options for meats, 4 options for cheese, and 3 crusts. So multiply them by all times each other, and that gives me 60. So I have 60 possible combinations for that pizza. All right, let's see. I think I'm going to skip a little bit. So then there's also a concept of factorials, okay? Factorials are used when you're trying to figure out, it's not outcomes per se, but say you're trying to figure out how to order or arrange letters, right? If you have 3 letters to choose from, say you could choose A, B, or C, and you don't care what order they go in. Actually, let's change this example. Let's do, actually, we're going to skip this part. Skip this part right here, okay? I don't think it's all that helpful. Let's go on to the examples, what you might actually see on the test. Now, when it says how many different ways, this is where you're going to use your factorials. How many different ways can you do something? Okay, how many different ways can you do something? Then you're going to use factorials, okay? A factorial, all it is multiplying. I guess if you go back, it does have it here. Factorials, all it is multiplying numbers by the next number in order. So like 6 factorial, sorry, go back actually. I do want to show you this. 6 factorial, all you're really saying is 6 times 5 times 4 times 3 times 2 times 1, okay? Which equals 120. Now you can do it out, just punch it in your calculator. 6 times 5 times 4 times 3 times 2 times 1 equals 120. Or there is a little way to put this little exclamation mark into your calculator. Okay, we'll talk about that on the next screen. Okay. Now, how they would be used in real life are factorials are used when it's trying to figure out how many different ways you could do something. Okay, how many different ways can you arrange these letters, A, B, C, D, and E? Well, that would be 5 factorial, because we have 1 option, 2, 3, 4, 5. So I'm going to take this, whatever it is, and do 5 factorial. Okay, now, again, this, and just doing it by hand would be 5 times 2 times 3 times 4. Why am I doing that all backwards? 5 times 4 times 3 times 2 times 1, and that equals 120. However, again, you can just type in 5 factorial in your calculator by going to Math, grabbing your probability, going to your probability menu, write it down, then we'll go through it. And then going to, I think on your calculators, it's number 4. Okay, the menu option number 4, and it has a little exclamation mark to help remind you that's what you're doing. Okay, so if we go to our calculators, we go to, where's my math, probability, and number 4, you see this little exclamation mark. That's your factorial. So push enter. Now I want to know, so I need a right arrow over to where that A is highlighted, or its cursor is flashing on it, and I want to know 5 factorial. So I'm going to type a 5 there. Then I just push enter, and it equals 120. Okay. So 2 ways you can find it. Now, using your calculator, when it's only 5 or 6, it's not too hard to do 5 times 4 times 3 times 2 times 1. But when you get up to one that's like 25 factorial, it's a lot to push in your calculator. You can still do it, but using this little exclamation mark does make it easier. Okay. Okay, so then we have another one. How many different 4-digit numbers can be created using these set of numbers? Well, this would be 4 factorial, because we have 4 different numbers that we're trying to use to make phone numbers. So 1, 2, 3, 4. So 4 factorial. Again, you can put in your calculator using Math, going over to the probability menu and selecting number 4, or you can do 4 times 3 times 2 times 1, which equals 24. Okay, so I want you to do let's see. So this one, how many ways, we'll just do it together. How many ways can 6 people sit in a row with 6 chairs? Well, that would be 6 factorial. 6 factorial, just plug it in your calculator, gives you 720. All right, the other last 2 concepts we can talk about this year are permutations and combinations. Okay, a permutation, way I remember this is you're taking a set of objects, and you want to know how those objects can be arranged. Well, or how many different ways can they be arranged. Permutations is when order matters. So if you think about it, I remember permutations are perfect. Only way something can be perfect is if order matters. The order is correct. So order is correct. Only way you can get something to be perfect is if the order is correct, and I just remember it per, and you want to be perfect if you're a permutation. Order is correct. Order matters. The other option is combination, in which case your order doesn't matter. Sometimes it'll say position, but order does not matter if it's a combination. Okay? Just think permutation is perfect. Order is perfect. Okay, and this, you can both do these on your calculator. These are the steps to do it for permutations. You're going to hit Math, probability, or give you these steps, and then we'll go over them. And then number 2, menu option number 2, NPR. Combinations, similar area, Math, probability, and number 3 for NCR. Right? Makes sense? C for combinations, P for permutations. Okay, so let's see. Alright, so it's just, these are just practice putting your calculator. I'll do a couple of you, and I want you to do the rest of these, and they will be due with your notes next class. But, so let's just do 1 permutation, 1 combination. Let's do C up here. Alright, so permutations. Okay, this would be like I'm selecting 3 people out of 4. 3 out of 4. So if I go here, go to my calculator, go to Math, probability. And you see it says NPR right here on number 2, so I'm going to scroll down and select 2. And then yours, you might have to, it'll say, I think, ANS, or it might just say NPR. You need to move over till you're to the left of where it says NPR, and you just put your number there, and then you'll move over to the right of where it says NPR, so where the thing's flashing right here, and put your other value there. Okay, whereas mine is a little different because it has little boxes. I don't believe yours does. Okay, so put in 4, and then put in 3, and push enter, and it equals 24. Okay, so this equals 24. All right, so I want you to solve A, B, and D. D, you'll need to watch this next example before you can do it. So D, let's do C here. Again, it's the same thing, you just pick a different menu option. So I'm going to go to math, probability, and I'm going to select number 3 or NCR. Okay, again, you'll need to move over to your cursor over, I believe, till you're in front of where it says NCR and put your value of 4 in there, whereas I put it in my little box because my calculator is slightly different. And then 3. Okay, and then I push enter. And it's 4. All right, so let's do some examples so we talk about what this really means. Okay, so that equals 4. So I want you to do A, B, and D. B and D, all it's saying is, I'll show you with D. B, all it's saying is when you go to put this in your calculator, it's going to be 10, choose 4. Okay, you can never, you can't go the other way with it, and we'll talk about why in our examples, but you can't choose 10 when you only have 4 options, right? So the larger number is always going to be first, and your smaller number will always be second. If you have it flipped around, then you have it wrong. So, okay. All right, let's see, which of these do I want to do? Pause this a second. Okay, so I'm going to do these first 2 together, and then the rest of them I'll give you hints on, but I want you to finish them. Okay, so the first 2. So the first one, there are 20 people who work in an office together. 4 of these people are selected to go to the same conference together. How many selections are possible? I don't care what 4 people go. They're all going to the same conference, so it doesn't matter as far as the first person's going to one conference, the second person's going to a different conference. It doesn't matter. They're all going to the same conference. So order doesn't matter here, okay? It doesn't matter who I select. I just need to select 4 people. So when order does not matter, then I use combinations. So I have 20 people. Remember I told you the larger number always goes first, and I'm selecting 4. So I'd have 20, and I'm choosing 4 of them. Okay, so I can type that in my calculator, and that would give me 4,845 options or selections for choosing 4 people. So 4 combinations of people out of 20. Okay. All right, the next one. There are 20 people who work in an office together. 4 of these people are selected to attend different conferences. The first person will go to New York, the second will go to Chicago, the third will go to San Francisco, and the fourth goes to Miami. This one order does matter because if I'm selected first, I'm going to New York versus if I'm selected fourth, then I'm going to go to Miami. Order matters. It matters what order I'm chosen in. So this one, remember, permutations have to be perfect order. Try to remember it that way. Okay, so I'm going to use permutations here. Again, the larger number always goes first, the smaller number goes second. So I have 20, order matters. 20, choosing 4, where order matters. Okay, and this, when I type in my calculator, is 116, 280. Okay, so there's a lot more options when order does matter. Okay. All right, so let me give you some hints on these. Let's see, serial numbers for a product are to be made using 3 letters. Okay, serial. Let me read. The serial numbers for a product are to be made using 3 letters. Okay, using any letter, doesn't matter. Followed by 2 numbers. Okay. An example, JGR 29. How many such serial numbers are possible if neither letters nor numbers can be repeated? Okay, so letters are, when I first start, I have 26 options for letters, correct? It's 26 letters in the alphabet. After I choose my first letter, now I only have 25 options to choose from. Choose the second letter, now I only have 24 options to choose from. Okay? Alright, and then I have how many single digit numbers? Well, I actually have 10 of them, right? Because 0 counts. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 10 options for numbers. So when I first start, I have 10 options. After I choose one of those 10 options, I now only have 9 options because they can only be used once. They can't be repeated. Alright, so then I multiply all of these by each other, because this is like when I'm choosing options for lunch, okay? I have 4 options. If you go back to that one example, I had 4 options, then I had multiplied by the next set of options, multiplied by my next set of options, okay? So that gives me what? So that's how you would set that one up. Kind of solved that one for you, pretty much. Okay, this one's like the example. Alright, so let's talk about this one. In a new group of 15 employees at a restaurant, 10 are to be assigned as servers, 3 are to be assigned as hosts, and 2 are to be assigned as cashiers. How many different ways can this assignment be made? Well, when I'm first starting out, I'm going to first choose my servers. So I have 15. I don't care what order they're in. They're all going to be servers. So the first 10 I choose are all servers. So it doesn't matter what order they go in. They're all going to do the same job. So 15, choose 2. Okay, it's a combination. Then, on top of that, so I'm going to multiply the next option. I now have 5 employees left, and I'm going to assign 3 of them as hosts. So I have 5. Doesn't matter what order they're in at this point. These 3 are all going to do the same job. So 5, choose 3. And then lastly, I have 2 left over and 2 assigned as cashiers. So 2 times 2, choose 2. Okay. When you put that in your calculator, you'll get that one. Let's see. Let's do another couple of these. Okay, so this one, how many ways can a first prize, a second prize, and 4 identical third prizes be awarded to a group of 15 people? Okay, so first prize, it doesn't matter, but I'm going to say 15. I have 15 options. Only one of them will get that first prize. Order doesn't matter. Whoever I choose gets first prize. It's not like order matters and only the first one picks gets this one, the second one picks gets that one. Okay, and then, oh, sorry, I was reading part of the other one. Nope, just kidding. And how many ways can a first prize, order does matter here, right? Because if I choose you first versus choosing you second, and I write a C again. Choose you first versus choosing you second, that matters, because if you don't get chosen first, you're not going to get first prize. Okay, so order does matter. Okay, next one. I now have 14 people to choose from. Someone's already been selected out of my pool of people. So, and the next person, again, order matters. Next person gets second prize. If you don't get chosen second, you don't get second prize. Okay, order matters. Lastly, I have 13 people, and it doesn't matter how they get chosen, so it's a combination because all 4 of them that get chosen get identical prizes of third prize. Okay, so the last one's 13 choose 4. Put that in your calculator. Okay. There are 10 students from whom, next one, number 7. There are 10 students from whom 4 are going to be chosen to represent their school at a conference. If Jack, Anna, or Chris, but only one of them must be chosen, in how many ways can the students be chosen to go to the conference? Okay. So basically what it's saying is a little confusing the way it's worded, but basically what this is saying is I have 10 students. The first person chosen will be one of these 3 students. Okay? After that, I will have 7 students from whom it will not be one of those 3 because only one of those 3 get the first spot. Then I have 7 other students who will go for that second spot that are going. Okay? So the first one is I have 3 students. For this first spot, I have 3 students, Jack, Anna, or Chris, and I'm choosing one of them. At least one of them will go to that one conference. Okay. Then after that, none of those 3 can be chosen for the second spot. So the second spot, I only have 7 students to choose from, and I'm choosing 3 of those 7 that are left over. Okay. Okay, next one. Pete has 5 different ties that match with 3 different shirts. All right, I'm gonna let you work that one out. And the last one is a factorial one. Remember factorials? We talked about that. So you can go back to that part of the video if you need to. Okay, that's it. I hope you all have a great weekend. Don't forget, SOL start next week. Please come to SOL review on Mondays. You need to finish these last few that we didn't do together and the few that during the notes that we didn't do together. And I will collect these notes next time, so make sure you have them. If you finish this in class today, you have no homework, so have a good weekend. Other than remember your options for studying for the SOL includes review on Monday afternoon with Miss Short and myself from 2:15 to 3. And don't forget we provide snacks. May 16th is Super Saturday. Don't forget to go to that and sign up for it because they do provide food. And then the third option, if you work and you just can't get into coming to either the Monday afternoon review or Super Saturday, remember that there are videos, SOL review videos on Blackboard that go through the previous year SOLs, and they don't change the questions all that much. So make sure you take advantage of all opportunities. We only have a week until our SOL, and if you pass, you are pretty much done for the year. So keep that in mind. Spend the time wisely and make it happen so that you can be done. All right, have a good weekend. See you next week. Bye.